Okay, I guess we can get started. So the next talk is from Ludovic Gillet, who's a staff scientist or senior scientist in the Aerosol lab, and you probably already heard his name mentioned a couple of times in the context of SWATH development. And I also showed some of the data I showed yesterday in the introductory talk was from this first paper in 2012 that was written by Ludovic. And so what he's gonna focus on some of the data analysis techniques, in particular how to do peptide-centric analysis, peak picking, scoring, and false discovery rate estimation. And we're going to have a second talk after this from Isabel, which is going to do the second half of this kind of double act. So, Ludo, please.
Thanks, Ben. Hi, everybody. So this talk here is supposed to bring you some background about how we identify and score the peaks and how we define the false discovery rate in the context of targeted proteomics analysis of these DI data sets. So the idea is that this part of the tutorials and of the knowledge sits after the DIA acquisition, after you also generated your libraries as you did yesterday in your tutorials, and after you perform these chromatogram extractions. And I'm going to explain you today how you perform actually the peptide identification. So one point here is that in DIA compared to DDA, the peptide identification is intrinsically linked to the label-free quantification. So as soon as you identify your MS2 peak shapes in your chromatograms, you can basically derive from it a label-free quantification. So this is really a very crucial point, and I'm going to explain you, especially in the context of the decoys, and in view of what you heard this morning from Mike, that actually the way we actually do the decoy scoring is also in this concept of peptide-centric, and you will see that it has a very different meaning and basically implication that when you do decoys, for example, for DDA database searching. So this is a slide I think that you have seen yesterday from Ben, and basically, so this is what we call this type of comprehensive MSMS acquisition. So each of these windows is this isolation. Each of these arrows is the isolation window that you have in DIA type of methods. And basically, what we focus on when we do extraction chromatograms is on a specific window. So this is what we call a SWATH. This is this slice of mass spectra. And this window here, for example, 600, 625, as an example, gives you access to another dimension in the data. So while you might be used to see this type of MS1 maps, where you have the chromatograms and the M over Z of the precursors, this is actually what we are looking at when we do SWATH or DIA analysis, is basically MS2 maps. As you see here, it looks quite different. So the axes are the same. You also have the retention time of the chromatograms and the M over Z, which is recorded by the mass spectrometers. But here, each of these points is a fragment ion. Okay? And as you can see here, you have now not anymore defined precursor patterns that you identify as you see in the MS1 maps. Here, what you have are basically tracks that belongs together, and these are basically belonging together because they are the fragments that came from the precursor that was eluting at this retention time in this mass window. Okay, so you see these big patterns, these vertical patterns of masses. These are all the fragments that comes from the same precursors, that fragments, and then they give this trace in the chromatographic dimensions of that peptide upon fragmentation. So the way, as Mike alluded this morning, it's very, very complicated maps. You have coelution, co-fragmentation of many precursors simultaneously. And the way we suggested to use originally this data, to extract this data, was to go for spectral libraries. So the spectral libraries can come from DDA, spectral libraries can come from DIA, as Mike suggested this morning. The idea is that you have a set of masses which are unique to your peptide of interest. So this is very important. This is what I call unique ion signatures. So this unique ion signature should be a set of masses, of fragment masses, which are exclusive of this peptide for your organism. And this set of masses, then you can use exactly as you would extract the mass of the precursor in the MS1 map. You extract the mass of these fragments in the MS2 maps. So you extract them with certain tolerance. This is in the range usually of ppms on modern instruments, so like 10 to 20 or 30 ppms. And what you do here, you check these masses. Is it present in this chromatogram map? Is it present here? Is this mass present here, etc.? So as you can see, for example, the mass of these fragments at 855, the red trace here, is absent at the beginning of the chromatogram. And then at some point here in the chromatographic time of 40 minutes, there is some signal that comes out and then disappears. And then sometimes you have some other red signals that show up at some other times. These are some peptides also, which are also captured in this isolation window of 600, 625, that also by chance at some retention time points fragment, and one of their fragments gives as well these masses. This happens, of course, a lot of times. But the thing that matters a lot is that this, for example, in this case, these 5 fragments, these 5 unique fragments of masses, they happen to co-occur only once and a single time in your organism. And therefore, when they co-occur in the chromatographic dimension, this is an indication that this peptide is present, and it's eluting in this mass window, in this MS2 window, at this retention time. Okay? So as you will see here, this is actually a very important criteria that we'll use when we do the scoring and when we do the estimation of the assessment of the evidence of identification of these peptides. On top of that, so this is a type of data that you get typically when you do also PRM or SRM. And on top of that, of course, because it's DIA, you have extensive MSMS sampling. So you can also take the apex of the retention time of the apex of this peak and then open the complete MSMS spectra that you have at this retention time. And then you can confirm here, you basically have the correct fragment, etc. On the peak. So I'll show you actually how we leverage this information, both in the chromatograms and also in the mass spectrometry dimensions, and how we use this as scores in order to validate the identification of your peak. And the idea is that, so this you have seen in your Skyline tutorials already, so we work a lot with these chromatograms dimensions. And if you come from an SRM background, this is something that you might have done already a lot manually, or PRM. And this is something that Skyline was very, very good at helping people to do that. And you can visually inspect like hundreds of peptides in few samples. The problem that when you speak DIA, now we are speaking at hundreds of samples. Now we are even speaking at thousands of samples. And we are looking at 10,000s of peptides simultaneously. So there, the problem is that it's hardly possible to visualize and inspect manually all this data visually in Skyline. So we needed a way basically to make an automatic peak detection. And more importantly, it's not only to detect the peak, it's also to report an objective quality scoring for those peptides. And even more importantly is actually to be sure that we report these peptides with a certain false discovery rate, it's FDR. And therefore here, this is going to be the big topic of this talk this morning by me and Isa after me, that we really want you to understand these tools, the concept, and how we actually perform peak scoring and FDR assessments on these very specific types of data when do peptide-centric analysis of DIA data sets. So that's, again, some kind of a very simple scenario. And as you can see here, you have a very simple peak across your entire chromatogram, so it's quite obvious. There is absolutely almost no doubt that this is the correct peak. And therefore, you can confirm that the peptide is present in your sample. You can zoom, you can actually see, and this already gives you kind of a couple of ideas about the criteria that we'll use for peptide scoring. You see here what you have. You have the peaks here that collude with a nice peak shapes. All the fragments here, they elute with a similar peak shape, so you have a very good correlation between the peak shapes of the different fragments that you have here. You have a correct apex for the retention time, correct peak width, etc. So the chromatographic scoring is going to be a very important component of the scores when you do SRM or when you do DIA type of peptide-centric analysis. However, sometimes, as I already alluded a little bit in the first, the data is so complex that even though you extract unique and signatures, it happens sometimes by chance that the sample is so complex then this type of fragments, 5 fragments, they happen more than once in your sample set. So this is the case here. When you, for example, see that at this peak at 16 minutes, you have actually the fragments which are coming together. Y11 is a bit low, but might still be belonging to your peptide. And at 23.9 minutes, you have a very nice peak group. Here from the peak shape, from the collusion of the fragments, it would be very hard to tell them apart. So there you can leverage another level of information that you know from your DIA because you use a spectral library. So this is what you have done yesterday. And it's not only important to actually get to know the masses that you want to extract, it's also very important because you have inside two informations, the retention time of the peptide and the relative intensity of the fragments. So this is something then you can also use and leverage a lot in your DIA analysis. You look for your MS2 spectrum. And what you see in your MS2 spectrum, the most intense fragments, for example, would be a Y9. So then it's very easy to pick up that this is actually the Y9. Here is the highest, while here is actually the Y6. So already from this picture, and this is also a score that is very well implemented in Skyline that you can actually look it up. This is called the dot product. So the dot product is actually the correlations of the relative intensity of the spectral library to the extracted ion chromatograms that you have. So if you have a good dot product, you can basically reinsure the fact that this is the most likely peak here, and this is probably just an interference or something that just happens by chance. Sometimes, however, it's even more crowded. And sometimes, even if you look at the spectral library, you have actually potentially multiple peaks that actually score also very high in terms of dot product. So here you see, even if you take a dot product of 0.99, you still have a bunch of peptides that could potentially also represent a Y8, Y9, Y7, etc., that elute in the correct order, etc. So there, another alternative that you can do, and you can do this also in DIA as well, is actually to use a heavy label samples. So in this case, it's a yeast N15 label that you can use as a reference. You can also spike in aquapeptides. And the idea is that here again, you basically can overlay the trace of the light and the heavy. And as you can see, there is only one place here where the light and the heavy collude. And what you can open the individual transitions of the light. You can open the individual transition of the heavy. And here you see another set of scores that potentially pops up. So here, this is actually a very interesting that not only the light comes in the order of relative intensity of the transitions of the fragment ions as on the library, but you also have the heavy ones that have the exact order of relative intensity for the fragment and the light. So this is what we call in Skyline the relative dot product. And here you can actually leverage also this information in order to be sure that you actually have, you're dealing with the right peptide identification. So the peak shapes, the peak width, apex, relative intensity, all those are information that you can now fetch out from the heavy channels in order to feed back the relative confidence to the light channels. Okay, so you can still confidently identify your peptides in those cases. And we have some very good data where you have labeled DIA data sets where you can actually improve a lot the quantification, the identification confidence and the quantification accuracy. However, sometimes whatever you do, you don't see the light, you don't see the heavy, and then it's very hard. So you can say here, I don't see my peptide, but the question is always, how do you assess non-detectability? So here is actually a very different story as in DDA. So the thing is that if you know that your peptide should come with these transitions, with these fragment ions, and if you don't see them, you can be pretty sure that in DIA, you're extracting the right assays, but the fact that you don't see it means that your peptide is actually below the limit of detection of your instrument. So this is actually a very powerful information because actually, instead of having a missing value in DDA that you don't know if the machine maybe did not pick the correct precursors for identifications, here you can be pretty sure that the missing identification means that the peptide is really below the limit of detection of your machine. So what you can do, and this you will see also a little bit later with Isabel, you can fill up like background areas exactly at the place where your peptide is expected to come, etc. So you can fill up and missing values, etc. But in terms of identification, this is a very tricky scenario because how do you actually assess the non-detectability of some peptides? So with all these questions, basically I alluded already some scores, and I already alluded a little bit into the problems of how to assess the truth or the non-detectability of some peptides. And this comes into the story that, so now here I'm just going to re-summarize the different scores that we discussed together. So we have these coelution scores. When you see here one transition doesn't coelute, you have the peak shapes. Here they coelute, but you see the peak shapes form is different. We actually also like usually have an intensity scores that usually favors the more intense peptides if it's detectable. We also have what we call the extrinsic scores. So these are purely coming from your just looking at your data chromatographically speaking. Extrinsic scores are information that you use which come from external sources like libraries the expected retention time or IRT information, the correlation between your measured fragment ions and the assays from your library. And then you have the Plex scores that you can leverage when you have like spiked in peptides, heavy peptides. And here you can actually use the intensity correlation between the light and the heavy. You can use the coelution scores between the light and the heavy and the peak shape scores between the light and the heavy. So all these scores, they were actually derived. I don't know if you see the reference at the bottom here. This was actually the original mProfet paper that was originally, all these scores also exist, and they are used extensively if you do a high throughput SRM analysis with mProfet. So all these scores already pre-existed in mProfet. And on top of that, as I mentioned a bit earlier, you have a lot of DIA-specific scores that you can additionally add on top of those already important scores. So these are MS2 specific scores, which are only can be only detected in PRM or DIA dataset because you have access to the full high-res MSMS spectra at every single time points of your chromatographic peaks. So what you can check on top of it in your MSMS spectra. So these are also screenshots from Skyline. You can probably recognize, and you will use this information later in your tutorials. You will have you can check whether the fragment ion is accurate for the fragments that you extract. So you can see how well it sits in the middle of your extraction window. You can see are you extracting actually the monoisotopic, the monoisotope of your fragment isotopic pattern, or you actually extracting the fragments with the correct charge state. Is it a singly charged or doubly charged fragments? Are you having an extended YNB ion series that you can, on top of it, extend and confirm that this is the right peptide, etc. So all these scores are scores that come on top of these ones. And these are the ones I will show you a screenshot in Skyline where you do kind of an mProfet refinement of your identifications. You can actually see the weight and the power that each of these scores has in your very specific data sets with your specific library that you use for extraction. So again, all these scorings are fine. But we realize it's a little bit like if you go back in the 90s when people were doing DDA and were reporting X score from Sequest, these scores are fine, but they're not sufficient in order to assess the false discovery rate. So we will need actually to get, to be sure about the false discovery rate, an idea what's the chance that such events occur by chance. And so this would basically capture the sample complexity and the noise level, and we need extensively to correct for multiple testing. So the idea is here again, it's borrowed away from the DDA database searching that we will actually compare the scores of the target peptides to the scores of Decoys peptides. But here you will see that the way we do it is actually very different than in DDA. So this is the big difference that we have between the two components, and the implication in statistics is also very different. So the idea here that the decoys are also necessary to assess the quality of the peak scoring. And the way we generate the decoys assays are essentially the same as we do it for shotgun, but you will see that we deal with them very, very differently. So the way we generate this assay, we reverse the sequence as well, or we shuffle them. And the idea is that these decoys is very important, otherwise you're not really fair in comparing the decoys to the targets. They must look like your target in your scoring algorithms. So in other words, here, what we care about is that the decoys should have a similar Q1 distributions. So there is no point to compare a target in mass 500 to a decoy in mass 2000, where you know that in mass 2000 is very low crowded, right? So you want actually to generate decoys that are also captured in the same retention time and mass window as your targets are extracted. This is, otherwise you're not fair in comparing the noise levels. You want to also have them to have a similar Q3 distribution, so number of fragments, number of transition, relative intensities of the fragments of these decoys, and also a similar retention time distribution as well. So all those are important components because you want your decoys to be representative of a chance that these targets assay are random. So we also use decoys, and the original mProfet paper was about this in SRM or PRM. However, for those, you need to measure them in your data set. So this costs machine times, and usually people are a bit reluctant to implement this in the SRM assay. But if you do high throughput SRM measurements where you actually want to measure and provide an FDR to the journals that start to request more and more even for SRM, you will also need to implement these decoys assay measurements in your SRM measurements assays. For DI and SWATH, it doesn't matter because you can actually extract as many decoys as you can. So the machine has acquired the data, and then the way the target and the decoys that you extract is completely independent from the acquisition. And again, the main idea is that you want to assess the chance that the set of fragment ions co-elute by chance. And as you will see again, it will have a very different signification than the shotgun decoys that we use for FDR estimation. So this is a very simplistic examples. So this would be a target peptide. This is the mass of the peptide here. So you know the mass of the peptide, so it's telling you which MS2 map you want to extract it with. So mass 642, you want to extract it in the SWATH MS2 map 624 to 650. And these are 4 fragments of that peptide, right? So these are unique fragments. We check the unique ion signature. It should be unique as a set of 4 peptides to that peptide. So when you extract the data, it looks pretty clean. It comes at the right retention time. And it comes as a nice peak group. And there you can get a raw score based on this, as I mentioned a bit earlier, coelutions, etc. OK, so you're quite good about it. But the question again is how you assess the quality of this score. So what we do here on the side, what you can do here is basically you take the same peptide sequence and you reverse it. So here it's a pseudo-reverse, but you can do full reverse. It doesn't matter. So here you see the arginine is fixed, and the rest of the sequence has been written up the other way around. So by definition, because same letters of amino acids, you have the same mass of precursor. So you are going to extract it in the same mass window. But as you can see here now, the Y7 falls 1, 2, 3, 4, 5, 6, 7. It falls after the P. So you have P, A, V, G, A, R. While here, the Y7 was after the P as well. So it's after the P, but the mass was P, E, D, I, W, V, R. So you see the Y7 mass, even though we cleave it at the same number of the Y or B ions ladder, the mass of it is very different than here. Okay? The mass of the Y8 is different, the mass of the Y4 is different, the mass of the Y7 2+ is different. And you know that because it's a decoy peptide, like you would do a decoy database search, you don't expect this peptide to be in your samples. It's a ghost peptide that should not be present. But in DI, you can still extract those masses and see how it looks like. So that's, if you extract those masses, that's how it looks like. So you extract it in the same mass window, and you extract it in the same retention time window as well. And you see here, it happens by chance that some other peptides at some other retention time, they also fragment, and they give you some of these fragments, okay? However, in principle, at nowhere, there should be a place where the 4 fragments should coelute, by definition, because this peptide doesn't exist. However, it happens that maybe one peptide fragments give you these 2 fragments, another peptide also roughly coelute with this one and gives you 2 other fragments. So the software doesn't know if it's a target of a decoy peptide it is extracting. The only thing it tries to do is to get you the best peak it can find in the chromatograms. So here it was clear, it was this peak, and here you see the arrow here, it's telling you it got this peak as the best scoring peak in that window. Okay, so the peak doesn't look as nice as this one, but it still has about 3 out of the 4 transitions. And as you can see here, the peak shape looks pretty decent, so it also gives a raw score. Okay? And all the trick is now you want to compare the scores of your target peptides and the score of your decoy peptides. Yeah?
I have a question. You were mentioning before this doesn't work for PRM, right?
No, it does. So
okay.
Yeah, it does as well. So for PRM, the only thing is that you can extract as well. So in PRM, you don't need to measure. Sorry, in SRM, you need to measure them because in SRM, you actually need to sit on these different transitions. In PRM, you can just extract them from the data as well. You're going to extract wrong masses that are not the one from your peptides, but you're extracting them by default in the same precursor and in the same window of retention time. So in PRM, it costs as well with no cost. And in SRM, it costs with a cost. Yeah.
Thanks.
Thanks for the, sorry. So here you want to compare basically the raw scores of the targets and the scores of the decoys. Yeah, oh, sorry, excuse me. Just shout, sorry.
Short question.
Yeah.
For decoys, the fragment intensities, are they the same like for normal peptide and expected?
That's a good question. Okay. Here I did not mention it. So here you see that what we do when we generate those decoys, we generate them using the original assay library of query parameters. And what we do, as I mentioned before, we just rewrite the peptide sequence. So the mass is new, but the relative intensity are actually the original relative intensity from the original peptide. So for example, if the Y7 had a relative intensity of 10,000, 6,000, 5,000, 4,000, we would have 10,000, 6,000, etc.
Thank you.
Okay, so this also gives you this randomness. And as you can see here, maybe this one here was the highest ones, while the blue here is actually one of the lowest one. And why it's maintained to be, in principle, should also be believed to be the highest one, it's also penalizing it accordingly, right? So the concept is that, again, you compare the raw scores of the targets and of the decoys. You do it many, many, many times. Of course, not comparing two doesn't work, so you have to do it statistically. And as you can see, for example, this is another example. The target peptide is actually hardly detectable. The highest peak it could find was this one. The score is very bad. And here, by chance, these 4 fragments happen and coelute quite nicely. So here, the coelution looks nice. Maybe the relative intensity to the assay library is bad, but at least the coelution is a very strong power as well. And here you see the score is actually higher than the target. So here you will have kind of a reverse plotting, where the decoy would score higher than its corresponding targets, okay? So it just happens by chance that these things elute or appears to be better than the target itself. And if you do this many, many, many times, you basically generate those plots. And this is actually how you compare the targets and the decoys distributions. So again, these are the mini scores I mentioned earlier. So on top of that, now you understood this concept of targets and decoys. So we are basically overlaying now the targets here in light gray and the decoys in black. And then you can see that sometimes you clearly see that some scores have already a stronger power than some other ones. You can already see that, for example, here the intensity correlation with the assays to your library has a dot product very close to 1, because most of the assays should have a good correlation. Whereas you can see here the decoys are basically flattened out. So basically the decoys score anywhere between 0 or -1 and 1, which means that they have a completely random distributions of relative intensity compared to the library assay, right? So what you do, basically, you can check those different plots. As you can see here, actually the highest scoring, the highest powerful score is the reference shapes, which is actually the correlation between the heavy and the light, which is the strongest scores that you can see in this plot here. Then you have the intensity correlation scores, which is the intensity correlation with the library, or you have the shape scores, which are basically the chromatographic, how well the fragments coelute together. So each of these individual scores is combined using this machine learning linear discriminant analysis. And what you do, you basically, each individual scores, as you can see here, for example, score 1 would not be sufficient if you would basically overlap and transpose this information on this axis. You would see the decoys and the targets would not very well separate. Same on score 2. Decoys and targets would not well separate. But now if you use kind of a linear combination of both scores, and then now if you project them to this green axis, you see that the targets and the decoys, they pretty well separate from each other. So this is in 2 dimensions. When we do this LDA analysis, we do it in n dimension. And this gives you basically the most powerful separations of targets and decoys that you can have. Okay? So again, this concept here was described in the M-Prophet paper. And this is basically the best combination and the best possible separation you can have between your true targets and your false targets in your data sets. So now what I want to come out is that the concept of decoys has a very different meaning in shotgun than in targeted proteomics approach. And this is a little bit what also Mike alluded this morning about this spectrum-centric versus peptide-centric. So this is actually when you do a spectrum-centric search of your DDA datasets, you get n spectrum, could be between 10,000 and 1 million if you search many runs. And basically each spectrum is assessed against a set of sequence that originate from the target or from the decoy database. So this is a very important concept, and this is now well understood in terms of DDA spectrum-centric search. So if you have good quality spectrum, it's a very, very high chance that you get actually the correct sequence from the correct target database. If you have kind of a medium quality spectrum, then the proportion already drops a little bit. In most cases, you should get the proper sequence, but it happens also the software will actually give you the wrong sequence. So if it's the wrong sequence that comes from the target, you will not know about it. But if it's the wrong sequence that comes from the decoy database, you will immediately recognize it. And usually this very, very bad quality spectrum, these are the ones that we call random hits. And by definition, because this will be assessed by the software as a completely random peptide that it will find anywhere in the database, by definition, it will be a random peptide sequence that it will be fetched from the entire set. So it will have 50% chance to hit by chance the targets and 50% chance to hit by chance the decoys database. So these bad quality spectrum have really this 50-50. And based on that, you can basically calculate the FDR. And this is the concept when you do decoy FDR estimation in shotgun, is that basically for every decoy sequence that you read in your peptide spectrum matches, you know that you have a hidden false target sequence as well that comes from the wrong hit of this kind of low quality spectra that fetched actually the target sequence, even though it was actually a wrong spectrum. Okay, so this is basically the main concept that everybody now is kind of familiar about the DDA search. And the idea is that the spectrum points either towards a target or a decoy sequence with a certain scores. And the decoys here really provide an estimation of the quality of the spectrum. And or, if you want, the chance that a random match happens between a measured spectrum and an in silico generated spectrum from your database. So this is actually very important because, as you can see here, whether you search one spectrum or 1 million spectrum, it doesn't matter. Each spectrum is only assessed against a set of precursors from the targets, a set of precursors from the decoys, which is only connected by the mass tolerance that you search your data. So if you search certain peptide with 10 ppm in your database search engines, whatever you search one peptide or one spectrum or 1 million spectrum, it will recover the exact same set of target peptides from target assay and the exact same set of decoy peptides from the decoy database. So the decoys here, they don't grow with the number of tests, they don't grow with the number of spectrum that you're searching, but they grow with the database complexity and the search parameters complexity. So now if you search more organisms, or if you search, for example, semi-triptych, or if you search phosphorylations, the database will increase in size for targets, and the decoy database will also increase in size for the decoy database. But again, whether you search 1 or 1 million spectrum, doesn't matter. You will extract from target and from the decoy the same number of tests. So this is a very important point, is that the number of decoys stay constant with the larger number of spectra that you're searching. For the peptide-centric DIA, the things is very different. Here, if you search one peptide, you're going to compare it to one decoy. So it's not going to work, but conceptually it's the same. And the premise is that the more targets you start to look for, the more decoys you need to generate. And therefore, you need actually to be very, very careful. What do the decoy capture at this level? So this is the picture that you saw a little bit before. This is the target peptide that is actually should be a correct peptide identifications. And here you see the decoys. What is it capturing now? It's not capturing the fact that this peptide is good or not. It's capturing the chance that there is noise in this region. So it doesn't tell you anything about that peptide per se. It just captures the fact that there is, because of your sample background, there is a certain level of noise and there is a certain level of chance that this, by chance, these 5 or 6 transitions, they will collude at some points of your chromatograms. So again, here, this is a very important sentence. The decoys provide an estimation of the sample noise or the chance that these colluting fragment traces exist by chance. So as you can imagine now, if you have a set of aquapeptides in water, or if you have a set of aquapeptides in a human background, the decoys will look completely different. Because in water, whatever you extract by chance, there is very little chance that you will have 6 transitions by chance that will show up in water. But if you have 6 transitions that happen by chance in human, it has a very different now meaning, right? So this is actually a very, very different part than the DDA spectrum-centric. The decoys, they capture the sample background complexity. And the number of decoys here that you have increase with the number of targets, which was also completely different than here. Okay? And therefore here, and you will see that it's important for my part, it's going to be even more important in Isa's part afterwards. You need to correct for multiple testing. So because then you're not exactly, these numbers constantly grow with the number of tests that you do. And you need to be extremely careful in order not to inflate your FDR by doing proper multiple testing corrections. Okay? But these are really, I think most people still trouble understand this part. When I send some paper for reviews. I'm still getting back reviewers that ask me, why don't I score my spectra against a decoy database? It's just conceptually very, very, very different, okay? So you have to understand the decoys in peptide-centric have a completely different meaning than the decoys in a database shotgun search approach, okay? So this is now also a very important point about these multiple testing corrections, is that in targeted proteomics, you cannot use decoy counting. So this was a very simple example that was done also by Lucas at the early days with mProfet. What we did, we basically took a human sample, we extracted 200 true human proteins and peptides, and we extracted 800 E. coli peptides that you don't expect to find in human, right? So you know those 800 are wrong by default because it's E. coli that you're looking for in human. And then on top of that, we extract these 1,000 peptides by reversing the sequences I explained you before. So the 1,000s are not expected to be there anyway. These 800 are not expected to be there, but you treat them as false targets. And these human 200 peptides, you extract them, and you consider them as true peptides. And as you can see here, this is the scenario, what happens when these distributions change when you do a 200 to 800 ratio of human E. coli, 500 human, 500 E. coli, 800 human, 200 E. coli, or 1,000 humans. As you can see here, these are basically the 200 human, and these are the 800 E. colis. Now you see here 50-50, the distribution basically they merge almost. And here you see the 20% E. coli, 80% human. And here you see the 100% human. And here what I want to point out is that, as you can realize, as Mike also mentioned earlier, the decoy and target distributions, they don't separate completely perfectly. And again, this is fine. This just means that some decoys, by chance, out of these 1,000, they look like real peaks, and then you have to accept that they're actually still reasonably well scoring. However, here, what is very important is that if you do a decoy counting, that would be completely wrong. You would start counting the targets. Here you would start actually counting the decoys. So you'd have here 5 decoys, 10 decoys, 100 decoys, and then you say, okay, here I have my 1% FDR, so I want to stop here. However, this is completely wrong, because as you can see in these two distributions, important is the fact that these decoys here, they're only worth capturing the false targets constants of your target distributions. And as you will see next slide, and this is what I mentioned about this correction for multiple testing hypothesis, because here you actually extract 0 false targets, which is 0 E. coli in your human background. You need basically to scale completely artificially this decoy into a 0 here, because there is nothing in the false targets that matches this distribution. And therefore here you can actually compare the difference if you have a decoy counting and the difference if you have a true target estimations, that you reach basically 100% of identifications of your 1,000 peptides with a 0% false discovery rate. So this is a big difference if you do a decoy counting when you start counting the decoys very early on. But the decoys here, they don't capture actually the proportion of false targets. The proportion of false targets here, it would be to this level. So here you can actually basically, you see these dotted lines. So the decoys here would be scaled down to the dotted lines. So you can estimate properly the FDR. Here the red decoys would be fitted out to the distributions of the false targets here with the dotted lines. Here you see that you would actually recognize the false targets here, and the false targets here basically flatten out, because there is basically no distribution here of false targets in your samples. So this is the big difference, and this is also how you cannot use decoy counting if you do peptide-centric FDR estimations, but you have to use actually a proper algorithm and proper theory in order to do these multiple testing corrections. So I already alluded a little bit how we do that. So basically the way we do it is when we have such picture of targets and decoys, you actually recognize under this distribution a certain proportion of false targets and of true targets. So these are the gray bars that you have on the bar. You can imagine them like a set of true and a set of false. And in order to do the proper FDR estimations, what you do, you have your decoys, which are actually much bigger than both, because they also contain, like, if you extract 40,000 targets, you also extract 40,000 decoys. but the 40,000 decoys, they don't capture actually the correct things. In order to use them for your example, for your sample analysis, you have to scale it down. So here, that would be the FDR that you would get by decoy counting. That would be wrong. So what you have to do is basically to scale down here the decoy distributions to fit. So now this is this dotted lines on red, which now sits on top of the false targets here. And only once you do that, you can actually do a proper matching of the FDR and a proper Q-value estimations of your peptide for discovery rate. So this is done actually doing, this is going to be the most complicated statistical part of this talk. It's done using an algorithm that was published in PNAS by Story and Tipshirani. And this is basically by plotting the p-value histograms, density histograms, and comparing now how it propagates and how is the error propagating. So this is an histogram, p-value histogram. So the total area of this histogram is basically 1. So here you see a p-value of 1 until a number of, so each of these bins is 005, 001, 0015, etc. And here you get until 1. So you get basically 20 bins. And this is basically the chance that your peptide is correct with a p-value of 0.05. And as you can see here, this is actually the case where you have completely random peptides, because none of them are actually correct, and they're basically their p-value are basically all anywhere between 1 and 0, but they basically have a flat distributions. So this is basically p-value distributions if you look at the decoys. Now, if you look at targets, of course, they should not look like this. So the targets would look something like this. So here the total area is still 1, but as you can see here, you borrowed some numbers, some p-values here in these regions, and you actually give them on top of here. So the total area here is still 1. And of course, now you have a much higher proportion of peptides that can be identified with a p-value below 0.05, so with 5% p-value confidence. However, you see here that distribution has a very specific characteristic. It flattens out. And the point here, you know that when it flattens out, this is actually corresponding to the basically accumulation of decoys. And this flattening out, you can actually project it now. And this tells you actually now the proportion of decoys that you have in your targets. So this is actually how we compute the FDR behind the scenes in mProfit. We basically take all the peptides at percent at 0.05 p-values. Then we plot this distribution of p-values. And what you do, you can basically project the distribution that flattens out and project, and it gives you an estimation of the decoys still present at p-value of 0.05. So this is how we transform the p-values to q-values. So we look at these plots. We find the asymptote, and then we basically plot the mProfit recall curves, sensitivity curves, and this gives you basically the conversions and the estimation of the FDR. So this is the kind of a mini wrap-up about this part. And so this is also important to understand the limitation that you have to take into account when you use this approach. The first thing is that so the first part of the method, as I showed you, is the combination of these scores. So this has a very important implication because of the machine learning. So the machine learning, the way it works, at least in the original mProfit algorithm, is that it tries to find, it subsets your data for good targets and subsets your data for bad targets. And it's learning from this original sampling of the data sets, the best sets of scores and the weight of these scores that best separate those, what it thinks are good and what it thinks are bad targets. And now here comes the point, is that your library, therefore, should contain a certain set of good and a certain set of bad targets. Otherwise, this machine learning just fails. Because then, if you provide your machine learning only with good targets, it will not be able to identify enough bad targets to learn this separation. Same if you extract only peptides which are not present in your samples, the machine will not train on good targets and it will not be able to separate both distributions. So it's important that you have, if you use this type of algorithms, to understand how they work and understand their limits, and therefore what you need to have in your library in order to be actually compatible with the algorithm that's used behind the scenes. The second point to be careful about is the FDR estimation. This is the second part I mentioned about the statistics. The Story and Tipshirani algorithms works only on normal distributions. So when you use these algorithms, please double check that your pictures look normal. So this is the pictures I showed you before. And as you can see here, the pictures of the decoys and the picture of the false targets and the picture of the true target should look like normal distribution and a sum of normal distributions. So this is a very strong hypothesis that was actually is necessary for these algorithms to work properly. The second point, as I mentioned very early in the talk, is that the assay should be homogeneous. You should have the same number of transitions or fragments for the targets and for the decoys. You should have the same distributions of mass windows, of time windows, etc., etc. So the decoys should be really representative. And so this, you see actually, if this doesn't work, or if you did something wrong in the way you generate your decoys, you happen to have something like this. So where your decoys, actually, the distribution of the decoys, they basically don't capture anymore very well the proportion of false targets. So you have basically a decoy distribution that gets decoupled. And as you can see here, if you try to scale down this yellow one, you basically will see that you will not be able to capture really the false targets that you have here. So this is very important when you look at these plots to understand what they represent and to understand. So you can see here as well, when you plot, for example, these p-value histograms, that this one flattens out, the blue one flattens out very well. But as you can see here, the blue ones doesn't flatten anymore. So it means that upon scaling of these distributions, you basically could not find a proper fitting of the false targets to these decoy distributions. And again, important point, do not use counting. It just doesn't work with this type of approach if you don't do proper corrections for the false targets proportion inside. And again, here, this is something that you will do in Skyline. Skyline is great. It outputs these plots automatically. And Prophet also provides you these PDF plots. So I really encourage you to look at those plots to understand what they mean and to really look by yourself if you think that the software has done a proper job in your samples. If it doesn't do this properly, like this, then you need to think about it and you need to try to understand what's going on. Maybe you did not use the right library. Maybe you actually removed some too bad peptides. Maybe, I don't know, your retention time was wrong or something like this. But it seems that your decoys here did not capture the real proportion of false targets. So again, this is the last point here. I think it's now all these tools, as you will see, they were command line based. So Brendan has done a great job to implement them in Skyline. So it's very easy and GUI for a click-on interface. So you can decide the number of decoy precursors. You can decide the way it generates the decoys. You will see them appearing as red dot peptides here in your Skyline target list. And you can reintegrate the peak. And then here you can basically decide the scoring models, the M-Prophet scoring model that you want to use. You can actually see each of the scores have a very different power and a very different strengths in separating the targets and the decoys. You see some are very strongly, the intensity scores, the retention time, but some actually even negative. So it seems that for this type of scores, maybe the decoys score even better than the targets, so it cannot be used, or at least they don't help to separate the target and the decoy distributions. So you can decide which scores you want to use. You can see the individual plots. You can see how they change the model plots after you remove some mini scores, etc., etc. So Skyline is very interactive if you want to if you have trouble and if you want to understand how the decoy distributions and the false targets, they basically compare to each other. So this is the wrap-up for this part. So I wanted to give you really like a background about this automated peptide identification. So we do target peak extraction of chromatograms, so we detect the peak in the chromatogram dimension, we score them. We also, I explain you how we generate decoys, how we do the decoy peak scoring, and how we run this FDR estimation per run at the moment. And Isa will give you a very nice extension to this when we run it on a per data set. And at the moment, this is really important that you understand this concept because it's this p-value to q-value and multiple hypothesis correction. And it's applicable to any targeted chromatogram-based methods. So I mentioned SRM, PRM with a correction I mentioned later on can be done easily. And I think if you have a large, high-throughput data set, I really encourage you. And now, like journals, start to think about implementing as well FDR estimations for targeted proteomics measurements, especially when you speak about big data sets. So this is the software is running in the background of many of the tools that you're going to use this week. So I mentioned about some limitation that you really need to understand, and I hope with this background gives you enough to understand the problem that can happen, this machine learning that needs enough good and bad targets, the Q-value and FDR estimations transformation that use proper decoys and use a proper FDR estimation. And again, I think also Mike mentioned this morning, I think if you have your ultimate candidate that shows up after your high throughput analysis, I really encourage you as well to look by hand and to confirm that those are real. These are not like a mispicking of whatever or noise or whatever. So this is really something, and for the Skyline is always a great tool because it's very easy to open like 20 files and look at this peak individually for some of them. And again, now this is on Isa's talk. We reassessed a little bit. So this was a very, very early days, let's say, of this work. So now we actually re-emphasize people that they should use a Q-value reassessment on a per data set level, protein FDR estimation, this came out from Ben and Isa's work, and also a cross-run alignment that helps also to gain correctness and confidence in identification and completeness for the data matrices. So this is the part that Isa will just now speak about. So stay with the future steps that we do in this field.
Okay, great. So any questions for Ludovic about Lawrence? There's a little bit.
Hey, Ludo, thanks. I just wanted to clarify one point because you were making a very strong statement against decoy counting-based FDR approximation in these types of data sets. Because you say it does not capture the fraction of false targets among your queried assays. But this concept is being applied and employed both in DDA and in DIA.
If you do proper scaling, yeah.
Exactly. So if you do the scaling, it actually is producing very similar outcome as what Isa is going to present. We made this comparison. So I think the decoy counting you were referring to is the naive decoy counting where you do not correct for these ratios.
Correct, yeah.
Okay, thanks.
So this is important to correct. Also a nice paper from Mike about this when they did this early on the shotgun where they do these corrections for false target. I think this is something which is very, very important. I don't know if Mike you want to comment. So this was done already early days.
Probably the better person to talk about it, but it's doing high zero correction.
Yeah.
Isabel will talk a little bit about that.
Okay, great. And anything further in terms of questions? Oh yeah, go ahead.
I wanted to ask, what would be the minimum library size and the minimal number of decoys? Okay.
Just stay with us. One more.
Okay. Then another question probably.
Yeah.
There is something like a pi profit. Is it similar to M profit or is it really different?
Are you covering it too?
Yes.
So M profit. So I mean, it's confused. I know, like many people are confused with the name of profits coming from the aerosol. So we have the original peptide profit that is DDA database spectrum-centric. We have the protein profit, which is for protein grouping and understanding the protein inference. We have the X profit for cross-linking, and the original M profit was for MRM. So that's the original M profits. As I mentioned, it contains only the chromatogram-based scores, okay? And since then, we have re-implemented in Python, and we call it PyProfit, and it's capturing all the MS2 additional scores from DIA, basically. Okay? You want to...
No, so basically, PyProfit is just a re-implementation of mProfit in Python, including the additional DIA scores. And now there's like an extension to the original PyProfit, which
how do you call this one? So
I mean, we still call it PyProfit, but internally we call it Jumbo PyProfit because it's a little bit generally bigger, and it includes like a cross-run integration and protein level and so on. And I'm gonna cover this. Exactly.
Then Skyline is based on mProfit or new version PyProfit or something?
So I think it's basically like the general pi profit because it also includes these DIA scores. So it's M profit plus extra scores.
Okay, thank you.
Exactly.